about this last time? What's a good use? What's a time when you want high frequency to go one way and low frequency to go another way? Speakers, right? So high frequency is higher pitch. Which speakers do those go to? Yeah, the smaller speakers, right? Low frequency would be your bass. You want that to go to your bigger speakers, okay? But you'll notice when you have a signal coming in from, your TV or whatever your audio system is, it's just one wire, okay? So the signal includes all the high frequencies, all the low frequencies, and if you want to distribute them to different speakers so that they're sent to the right place, you have to find some way to sort out the ones that you want to go one way and the other way, okay? But they all come together. So filters are a really good way to do that. Filters are also a good thing if you're doing experiments, and let's say you have a particular type of noise, right? You have a signal that you don't care about, that you want to get rid of, and you know where it lies in the frequency range, then you can filter it out, okay? So filters are really useful in electronics. The main application that you're going to be familiar with is speakers, but there's lots of other uses, and if you take an electronics class, they'll go into that in more detail. It's also band pass filters, so you let a certain amount through, or you can block a certain amount out. That's the idea. So let's talk about how this works. All right. So remember, let's think about what is the peak current for each of these things. So remember, if we have the reactance of a resistor is just R, okay? Because when we talk about AC circuits, we no longer talk about just resistance, okay? Inductors and capacitors also provide a kind of resistance. And we are pretty familiar with how an inductor would provide that kind of resistance, but for capacitors, it's just going to be the response to a particular frequency. So inductors and capacitors have different frequency responses, which means they provide different resistances at different frequencies. And we call that the reactance, okay? So the resistor's reactance is just resistance. That hasn't changed. That's true in both AC and DC circuits. But I write it like this because I want you to start getting familiar with the idea that in AC circuits, resistance is reactance, okay? So the reactance of a resistor is the resistance. But back in DC circuits, there was no resistance from a capacitor, right? There was no resistance from an inductor. So we didn't have to worry about that when we were dealing with Ohm's law. Now we have reactance. So resistors have a reactance, capacitors have a reactance, and inductors have a reactance. And the reactance of a resistor is the same as it was before, but now these other two things have it too. So every time you would normally put resistance, we put X now, okay? So X of R, just R. So the resistive reactance of a resistor is the resistance, which is kind of, anyway, that's why that's there. It's an overly long explanation. What's the reactance of the capacitor?
R.
XC,
Yeah.
which is what? 1 over omega times the capacitance, okay? So if you have a capacitor that you plug into your circuit, you read its value, and you can figure out its reactance based on what frequency your input signal has, okay? So what's the peak current going to be? How do we find current over here? Let's say these were both resistors. How would you find the current? Ohm's law, right? So V, and remember we're doing peak stuff now, so big V equals big I times whatever your equivalent resistance is. In this case, we're looking for an equivalent reactance. How are these things configured? Series, okay? So how would you get the equivalent resistance or the equivalent reactance? Yeah, you add them up, right? So you get R, X sub R, plus X sub C. It's not any different, but just to sort of walk you through the idea. So would be voltage divided by equivalent reactance. Okay? In this case, current is voltage, which is this epsilon naught. Okay, then it's the peak voltage, so it's the maximum amplitude. Right? So peak voltage divided by x sub c, which is 1 over omega c plus r. Okay? Okay, so what happens to this when the frequency is very low? All right? So let's think about this. When the frequency is very low, what happens to this thing? It's going to get big, okay? Because if we have this low frequency in the denominator, that means this whole thing gets bigger, all right? So that gets big, which means this thing, which is always the same, would be relatively small. Okay, so this resistance is going to be smaller than this resistance. So this gets smaller, this gets bigger, and we can say if it gets really small, you can say this goes to infinity, and that becomes basically just epsilon naught over x sub c. Okay? And if this is really big, then this becomes about 0. Okay? So all of this basically stops the current, which means that when you look at the voltage, right? If this, let's say this has a peak of 5 volts. What does this have? Because remember, we have to do loop law, right? So if this is 5, what goes across this? What goes across this?
0.
0, right? So that means all of the voltage drops across the resistor. Okay? Cool. What happens if the frequency is very high? What happens when this is a really large number? And that gets really small. That means this goes to 0, and that means you just get V equals IR. Okay? So that means your current, right, is going to be largest across your resistor. Okay? So we can see depending on the frequency, the voltage across each thing is going to be different. Okay, so if you have very high frequencies, you're going to have something happen where you shift the balance between the resistor and the capacitor versus very low frequencies. Okay? So let's go back to phasor analysis. So how do we look at this in terms of phasors? So here's sort of a procedure for doing phasor analysis. So start by drawing a phasor for the current. Okay? You can draw that wherever you want. Let's say, for instance, in a series circuit, and this is a series circuit, what do we know about current? Yeah, it should be the same through everything. So it's always going to be the same through all of your circuit elements because you're in series. Okay? So we don't pick the angle. We don't have to worry about what the angle is. Then we draw the voltage should be in phase with the current for the resistor. Okay? Because remember, a resistor doesn't change the phase of things. All right. Where do we draw the voltage across the capacitor? Now remember, with a capacitor in an AC circuit, the current leads or lags the voltage? Leads. So where should you draw VC?
Perpendicular?
Perpendicular, yes. So 90 degrees before or after?
Before. Well,
After, because
yeah.
Behind, right?
Yeah,
'Cause the
yeah.
current leads. So the voltage lags. Okay, so that means you put 90 degrees here. Okay. How do we figure out what our source voltage is from here? Epsilon naught.
E naught cos
instantaneous values, this is how they're going to work. And this is what I mean by that is, remember, the instantaneous voltage for the resistance should be here, right? The instantaneous voltage for the capacitor is here. So now we're using it to find multiple instantaneous values. The instantaneous value for the current is right here, okay? So the current's going to be in phase with the resistor, it's going to be out of phase with the capacitor, and if you want to figure out what your source voltage is for these things, you just figure out where these two sum. And we can use the parallelogram method where we just connect the dots here, and that's where that vector should point. Okay, and this is just vector addition. We're pretty familiar with it already. And so the length of this thing, okay, this is the length of your source voltage, should be equal to this plus this in vectors. So, from the magnitudes, what's the length of this thing? What do you use to find it? What math?
A squared plus B squared equals
Yeah,
C
it's
squared.
Pythagorean theorem. So this is going to be the square, this is the square root of BC squared plus VR squared. And how do you find the angle?
Omega.
Well, remember, this is your source voltage, so what's the angle from here? Just omega t, right? So this angle is omega t. So, we get this relationship for our source voltage and our instantaneous voltages that looks something like this. Okay, so for the peak values, you get this. Epsilon naught squared has to be equal to the voltage across the resistor squared plus the voltage across the capacitor squared. Now, how is this different from loop law in DC circuits? What did we get in loop law? Were these things squared?
No.
No. It would just be this plus this minus this gives you 0. Okay? But now, because we have AC circuits, the best way to figure out the voltages is to add the phasors, because the thing about loop law is loop law does still work in an AC circuit, but it's instantaneous, which makes it really hard to measure because you'd have to basically freeze the circuit and measure all the voltages at a particular time. Okay? They're all changing with time, and they're not in phase. So even though if you add up, if you freeze time and you add up the voltage across the capacitor, the voltage across the resistor, and the voltage across the source, you will still get that to add up to 0. It's pretty hard to do in practice, okay? So we do this math so we can figure out the relationship between the peak voltages without doing this instantaneous measurement. All right, so here's the peak values. And so that means, there's a lot of math that happens here, so you can plug this into V equals IR, and V is equal to IR where R is now X, okay? So just to give you sort of the idea of what this ends up looking like, all right? So this is V equals IR. You have to use this to get, we just start from this and get I, obviously, because I goes away, and you end up with this, okay? There's a lot of math. We can go through it if you want to at some other point, but just to sort of follow, you don't have to like furiously copy all of this down, but because remember, this is going to be different for each situation, and I'm only showing you this because it's going to, if you trust me that these are the values, okay? So, like, for instance, what is I?
Current. Yeah, peak current, I mean. Oh.
How did we find I?
Oh.
So from here.
Volts over the resistance.
Yeah, V equals IR, right? Remember, we did this earlier. So what, for the full circuit, right, when we deal with epsilon naught.
plus capacitance.
It's going to be equal to I R plus 1 over omega C. Right? That was our that's our reactance. So reactance of the resistor plus the reactance of the capacitor, they're in series, so you just add them because they're like resistors. And this is epsilon naught. Well, if we want I, okay, we know that epsilon naught has to be equal to VR squared plus VC squared. So you can see where this,
The square root comes.
I'm not going to go through the whole math, but you can see where the square root comes from. Okay, all right, good. So we end up with this epsilon naught, and then we can solve individually for V sub R and V sub C. Okay? So what happens when omega gets very small? All right, what happens here when omega is really small? So what happens to this term?
It becomes infinity.
It gets big, which means it's probably bigger than this, right? Which means this whole denominator is big. What happens to this whole thing then?
Turns into nothing.
It goes towards 0. Not exactly 0, but it gets pretty small. Okay? So if this gets small, this gets big, which makes this whole thing small. All right. What about over here? What if omega is small? So this one's a little trickier. This is small. That means this is big. Okay? Which means you can neglect this. So this becomes 1 over omega squared C squared, which is large. Okay? Basically, we just use that to get rid of the resistance. Outside here, though, you have another omega. But that's going to be omega divided by omega, which means the bottom thing is pretty much just, well, omega C, right? So you get omega C divided by omega C. That gives you 1. What are you left with? Just epsilon naught. So this thing goes towards epsilon naught. Okay? So in the case where you have omega very small, right, where you have a very low frequency, that means the voltage across your resistor is about 0, and the voltage across your capacitor is about the same as your source voltage. Okay? What if omega is really large? What happens to this thing? This goes to 0, which means you end up with epsilon naught times R divided by square root of R squared. So that goes to epsilon naught. And then, what do you think happens to this one without?
0.
Well, not 0, but small. So approximately small. Okay? So let's look at what this might look like graphically. And this is when you'll see why I did approximately and not 0. Okay? So for the capacitor, it starts out at low frequency, right? We said that it should be at about epsilon naught. And then it goes towards 0. It gets small. Okay? So this is what the actual graph looks like for the capacitor. And for the resistor, we know it starts out at 0, and then it goes towards the maximum voltage, epsilon naught. So it looks like this. Okay? Because remember, this is your peak voltage. You can see it doesn't quite reach it, but it gets pretty close. So most of the voltage ends up at the resistor at high frequencies. Okay? So the capacitor voltage approaches epsilon naught as omega goes to 0, so you get it up here. The resistor voltage, as your frequency gets larger, approaches your source voltage. Okay? And what do you notice about these graphs? Do you think it's significant that they cross here? Yeah. And we have a really clever name for this. It's called the crossover frequency. Okay? And it's represented by omega sub C for crossover. All right? It's called the crossover frequency. So just to sort of go over what that means, the crossover frequency, that's the frequency at which VR equals VC. Look, VR, this is voltage, so VR equals VC. They have the same value. Okay? And it turns out the crossover frequency is 1 over RC. Now, you can do some math there, but if you go back to this previous slide where we have this values for VR and VC, you basically just set these equal to each other and you solve for omega, and a lot of stuff cancels, is the short story, okay? And you get this really nice thing where omega C is equal to 1 over RC. Now remember, RC has units of what? When did we see
For
RC
what?
before? What was it equal to? Tau, which is a time constant, which means it has units of seconds. So 1 over RC has units of,
Seconds.
well, radians per
Radians.
second apparently. Okay. But yeah, remember radians is a weird unit that sometimes exists and sometimes doesn't. So I apologize in advance for that. But let's try a question. Either yes or no. Some votes for D. Please discuss. We'll vote again.
I like that plus.
Oh, yay. Good discussion, guys. So the answer is no. And why?
Because it's not square.
These things have to be squared, right? These are peak voltages. And what do we know about the peaks when we have a capacitor in an AC circuit? Do they happen at the same time?
Oh, no.
No, right? So if you just add them up at a time, it doesn't work, okay? If this were the instantaneous voltages, this would be true. But since these are the peak voltages, not true, okay? All right. So in practice, this is how you make a low-pass filter, okay? Here's your input voltage, right? And here's your RC circuit. So you put a signal in here, and you take the signal out only across the capacitor, okay? So this transmits all frequencies that are less than the crossover frequency and blocks frequencies, mostly, that are greater than the crossover frequency, okay? And obviously, if you get close to the crossover frequency, it doesn't work quite as well, but it transmits frequencies that are less than the crossover frequency. So low frequencies, say low pass filter, it passes the low frequencies, okay? Yeah. Any questions about that? How do you think we make a high pass filter? Yeah, you take your output voltage across the resistor. So you just flip your resistor and your capacitor, and this transmits high frequencies. So it allows high frequencies to come through. So all frequencies above the crossover frequency are allowed through, and it blocks frequencies below the crossover frequency. Okay? And how do you determine what your crossover frequency is?
1 over RC.
Yeah, so what do you change if you want a different crossover frequency? Yeah, R or C. So if you want your crossover frequency to go up or down, you just change the values of your resistor and or your capacitor, okay? So you can design your filter so that it specifically blocks at a certain point, okay? So let's say if you want a certain range of sound to go to your high frequency speakers, to your, what are those, tweeters? If you want a certain frequency to make it to the tweeters, you pick your RC circuit so that the crossover frequency starts to send stuff at a certain frequency, okay? And so you can design filters so that they have different crossover frequencies. And that's why it's not given in terms of an absolute, right? It's given in terms of the crossover frequency. And how you set up the circuit, which circuit elements you use, determines what the crossover frequency is. Okay? All right. So we're good for today. And enjoy the rest of your day. Sorry you had to come in so early.